All right, in this video I'm just going to give you a quick introduction to one of the main applications of differential equations, which is exponential growth and decay. You can see this all over the place in engineering, physics, biology, sociology, I mean anything. So the key thing is this idea is exponential growth. If you think of exponential growth, what does that mean? That means that the rate of change in the size of some population or sample or something, temperature even, is directly proportional to the size of that population or sample or whatever we're talking about. So if P is the thing that we're talking about, say P is a population, as you see it the most common, right? The change in the population over time is equal to some constant times P. So it's always proportional. How fast the population is increasing depends on how big P, the population, is. Whenever you see something like this, you're always going to end up with this sort of differential equation. You see right here, dP dt equals K times P. And we're going to have to solve that. What do we get then? So we're looking at like dP dt equals Kp. That means that K then is the relative growth rate, what we call it, which just means it's the percent change in P over time. So, if it's growing at a 5% rate, that means that K would be 0.05. If it's growing at a 10% rate, it would be 0.1. You get the idea. Okay, solving the initial value problem with P0 equals P at 0 equals P0, we get this. We get this equation, right? This is our sort of basic exponential growth equation. P at some time t equals P0 times e to the kt. I went through in another video, in the video on introducing separation of variables, I went through why this is, how we go from this basic differential equation down to this explicit equation for P. It's pretty straightforward. You're going to see it over and over again, so you want to make sure you know what you're doing with it. Go back and look at that video if you're not totally sure. With this equation, if K is greater than 0, right, if it's a positive, which means that, well, K is this, right, so it means if P is increasing, then, well, right, then P is increasing. Duh, I guess that's kind of obvious. Right, if K is less than 0, if K is some negative number, that means, right, we have negative growth, or P will be decreasing. All right. Common problems, and I'm going to look at these in separate videos. I'm going to look at these separately, but these are the kinds of problems you're going to see all the time with differential equations and exponential growth and decay. First one is population growth. You've got some population figures for various states, and you're going to assume, they're going to ask you to assume that the population is increasing at a rate proportional to the size of the population. You'll have to find a formula for the population at time t, or you'll have to make up a formula to use to predict the population at some time t, or whatever, something like that. Radioactive decay. Radioactive decay is a good example, real-world example of exponential decay, right? It's decreasing. A sample of some radioactive element decays at a rate proportional to the mass of the sample. Given the half-life of the element, that's going to be like the time, th, by which the sample will have decayed to half its original mass. You'll have to find a formula for the mass of the sample at time t. And then last one, Newton's law of cooling, kind of a cool example. Well, that was a bad pun. That wasn't even meant to be. I'm sorry. I'm trailing now. All right, so Newton's law of cooling states that there's a rate at which the rate at which an object cools is proportional to the difference between the object's temperature and the temperature of the surrounding environment, which is kind of obvious, right? It just means that, the closer you are, the farther you are between the temperature of the object and the temperature of the environment, the faster the thing's going to cool, right? You put something in the freezer, it cools faster than if you put it in the refrigerator. So you have to do the same thing. You have to sort of, given some points, basically you have to find a formula for the temperature of the object at time t. There's one other one. Oh yeah, and then continuous compound interest. I talked about that in the previous video on separation. This is like the most common thing, and I talked about how we can use differential separation to go from the differential equation that tells us, for instance, that this one, that's where P in this case is like how much money I've invested in something, like, or and K is the rate of interest continuously compounded. We can go from that to our familiar equation, which is like P equals P0 e to the kt, P0 being our initial investment, P being the value of our investment at some time t. Those are the kinds of problems you're going to see a lot of. There's other things too that we'll see, but I wanted to show you these because they're the basics. Okay, so the next videos, I'll go through one of each type of these examples.